So here's another polynomial graph, and we see those features that we noticed before. Continuous, meaning if we liked we could trace it without lifting our pencil, and gets very negative as we go off to the left, gets very positive as we go off to the right, and it has these x-intercepts. Our function has these zeros. This graph has x-intercepts at -3, 0, 1, 0, and 4, 0. This is where f of x is 0. So if we actually plug in these numbers, f of -3, that's 1/4 -3 to the third minus 2 times -3 squared minus 11 times -3 plus 12. And we see that that really does work out to 0. Same with 1. 1/4 times 1 to the third minus 2 times 1 squared minus 11 times 1 plus 12. This one's easy. You could probably work out that arithmetic without a calculator. Right? 1 minus 2 is -1. Minus 11 is -12. Plus 12 is 0. If we plug in 4, 1/4 4 to the third minus 2 times 4 squared minus 11 times 4 plus 12. Again, that'll work out to 0. Okay, so these are the places where f of x is 0. Those are the zeros of the polynomial. Those are exactly the same zeros that we find if we factor. So we'll actually demonstrate that. That 1/4 is just going to be along for the ride for the whole factoring process. And we know that 1 is a 0, so let's divide that out. So we've got our coefficients are 1, -2, -11, and 12. 1 times 1 is 1, minus 2 is -1, times 1 is -1, minus 11 is -12, times 1 is -12, plus 12 is 0. So we've got 1/4 times x minus 1 times x squared minus x minus 12. But then this quadratic is easy to factor. It is indeed x plus 3 times x minus 4. It's especially easy to factor because looking up here, we already knew that those were going to be the factors. We really do get those factors when we factor this. In other words, the zeros that we see on the graph are exactly the same zeros that we get from algebra, which should not surprise us. But that raises a question. What does it look like if the roots have multiplicity? That's a big deal in the function. Hopefully it'll make some difference in the graph.